Hey guys, this is kind of the second lesson for where we're going here, and this video will end up being a lot shorter than the last since we've already got all the introduction out of the way, and it's going to also be very related to things that we've already done. In fact, where we're going here, force applied to a current carrying conductor, if you really think about it, it should make a lot of sense, right? I mean, what we did previously is we talked about how if there is a charge, like here we had a proton, going through a magnetic field, a force was applied to it, and we gave this equation here where force is equal to the charge times the velocity times the magnetic field times sine theta, where sine theta is indicating that to get a maximum force, the charge has to be perpendicular to the magnetic field. That is, the direction of motion has to be perpendicular to the magnetic field. If it was going the same way as the magnetic field, there'd be no force. And also, remember it's QVB, that means the charge has to be moving over here. If there is no velocity, if the charge is just sitting there, there is no force. So now, where we're going today, over here, the idea here is, what if, instead of putting a single charge through a magnetic field, right, going from north to south, what if instead I put a wire going through it and I put some current going through it? Is there a force applied? Well, logic would tell you yes, because heck, a current is just a whole bunch of electrons, right? It's a whole bunch of electrons traveling down the wire, right, at some speed. A whole bunch of electrons traveling down the wire at some speed. And so moving charges in a magnetic field, who cares if they're in a wire, right, or that there's more than one? There are moving charges in a magnetic field. A force should be applied, right? So I want to quickly derive the equation that we're going to use for this. I'm going to start out with the equation that we already have, QVB sine theta. Now, I want to get out of these terms of charge and velocity, and I want to get in terms of current and the wire's length. That way, if we're dealing with current going through a wire, it's a lot easier to be measured. So I'm going to use two other equations that I'm going to substitute in here. The constant velocity equation, velocity equals a displacement that you travel here, which is the length of a wire for an electron. It travels down the wire, so its displacement is the length of the wire divided by the time it takes, T. Also going to use the equation for current. Remember, current is the amount of charge that passes by, Q, in an amount of time, T. Okay? Now, quickly, the velocity substitution is very simple, right? I just take velocity and I plug in here. So now I got F equals Q times L over T B sine theta. All right? Now, I've got a charge right here listed, so I'm going to come over here to my current equation, and I'm going to solve that for charge. So current times the amount of time that you allow this current to flow equals the total charge that passes by, and I'm going to take that, I'm going to substitute that in for charge. So that will give me the equation that almost the equation that I'm looking for here. F equals IT times L over T B sine theta. Check it out. The times cancel out, right? One in the numerator, one in the denominator. They multiply times each other, so they go away, getting me the final equation that I'm looking for and trying to get to. F equals I, that's the current flowing through the wire. L, that's the length of the wire. B, the magnetic field strength. Sine theta. Okay? F equals ILB sine theta. So that says force equals the current times the length of the wire times the magnetic field strength. All right, so now we're going to work a few problems. This one, I got a 2.2 meter long wire. I'm experiencing a force when a line perpendicular to the Earth's magnetic field, which is actually relatively weak. It's less than, or it's a little bit more than half a millitesla. So the idea here, just to give you a setup for the Earth, is kind of odd. The Earth actually has its magnetic north pole at the geographic south pole, and the magnetic south pole at the geographic north pole, right? And so the magnetic field runs from north to south, and so you get this effect going on. This is the idea of, notice where the magnetic field is going, right? It's pointing towards the magnetic south pole. This is why whenever you're looking at a compass with a little magnet or something like that, it's pointing towards the geographic north pole. It's actually pointing towards the magnetic south, as kind of odd and confusing as that is. Now, if I'm going to align a wire perpendicular, right, to the magnetic field, that means that I need to have it aligned vertically. And let's deal with at the equator to where it pretty much is coming parallel to the Earth's surface. I need to have that wire aligned vertically from the Earth's surface. That way it's perpendicular to the magnetic field. Now, all that's just set up. This is just a plug-chug problem, right? F equals I, L, B sine theta. And let's plug in everything we know. Force, I know that. 4.9 times 10 to the negative fourth. Current, that's what I'm looking for. What is the current flowing through? So I'm going to leave the I there separated out. Length of the wire, we're told, 2.2 meters. So plug in my 2.2. Right? Magnetic field strength, there's the magnetic field strength of the Earth, 5.5 times 10 to the negative fourth. Sine theta, and this is sine of 90 degrees, which this entire entity right here is just going to be 1, right? And 1 times anything else is itself, so that means this entire entity doesn't matter. Just get rid of it, okay? So I, dividing everything over here to the other side, right, is going to equal 4.9 times 10 to the negative 4th divided by 2.2 times 5.5 times 10 to the negative 4th. Right? I get a current here. So after shoving into the calculator all those numbers, I come out with a current about 0.405 amps. But it looks like I got 2 sig figs here, so that's still just 0.40 amps there for 2 sig figs. All right. Now let's move on to number 2. Now number 2 is going to it's going to make us recall some of the things that we've already learned in the past, specifically from circuits. Here, and I might have to use an equation, if I remember correctly, that I haven't taught you yet. So you're going to be exposed to a brand new equation here, or I might have, we'll see. Copper wire with a radius of 1.2 centimeters and a length of 1.8 meters is hooked into a 12-volt battery and placed in a uniform 3.5 millitensile magnetic field. How much force will be exerted on the wire? Well, I mean, this seems, at first, how much force is exerted on the wire? It just seems like a plug-chug problem, right? F equals I, L, B, sine theta, right? It's placed in the magnetic field. It doesn't tell us how it's placed. Let's assume that it's placed perpendicularly. So let's assume this is 90 degrees, right? Let's assume this is 90 degrees, which reduces this equation down because sine of 90 is 1 again to ILB, right? Reduces that equation down just to that. Plug in everything we know. Right? I'm looking for the force. I don't know the current, right? I've got to leave that unknown. I do know the length of the wire, 1.8 meters, and I do know the magnetic field strength. It's 3.5 millitesla. That's 3.5 times 10 to the negative third Tesla. Right? Well, to figure out the force, I first got to figure out the current. Well, what equations do we have for current? Well, we have Ohm's law, right? Because I am told a voltage here, right? I got D equals IR. That's 12 equals I times, now I hit another brick wall, I don't have R. So what can I use to solve for the resistance of this wire, right? So then I can plug into this equation, right, and solve for current, plug in over here. So remember back to the base current equation. R equals the resistivity times the length of the wire divided by the cross-sectional area here. All right, let's use that equation to solve for the resistance, so then we can plug in Ohm's law and then plug back into our force equation. All right, so copper has a resistivity of about 1.68 times 10 to the negative 8 here. Okay, I'm going to take this entire thing and move a little over so I got some room. All right, so that times the length of this wire, 1.8 meters, 0.8 meters, divided by the cross-sectional area. Now, I'm told a radius, and if we assume that this wire is a cylinder, that means the cross-sectional area is a circle, so we're going to use pi r, which is 1.2 times 10 to the negative second, because it's in centimeters, right? Pi r squared. Okay, so that's going to allow us to plug into our calculator and get a resistance. All right, so we end up getting a resistance of 6.68 here. 6.68 times 10 to the negative fifth. And that's really small as well. It should be. I mean, it's a wire. We don't want a wire here to have a high resistance. This isn't a resistor. This isn't a wire in a toaster that's meant to get hot. This is a straight copper wire. It's meant to transmit the electricity without stealing any of the power. So the idea is you're going to want to keep that resistance very low. Now, this is going to allow me to take this number, right, and plug it back up in here for the resistance. So let's kind of give myself a little bit of area here. So I'm going to end up with my current, I, is going to equal 12, right, the voltage, divided by that resistance, 6.68 times 10 to the negative fifth. So we shove that to our calculator and get ourselves a current here of 1.79. Let's see what's going on here. All right, 1.79 times 10 to the fifth amps. So here's my current, right? Well, finally, I can take that current and shove it in for I now, right? So I'm finally down to my last calculation where my force is going to equal 1.79 times 10 to the fifth times my 1.8 meter long wire times the magnetic field strength, 3.5 times 10 to the negative third. So just another last plug chug part in the calculator, and we come out with a force. All right, so we can get a force of about 1.1 times 10 to the third newtons. The interesting thing about this that actually comes into play here is for a small magnetic field, right? We're in millitesla. For a small magnetic field and a small battery, a 12-volt battery, right? If we just use a standard wire, we get enough current through that thing that there's actually a very large force that's being exerted on it. So this is kind of the idea behind railguns and other things that we'll talk about later, because it's such a large force on that wire ends up moving relatively fast. All right, so now let's do one last problem here. The wire carrying 7.4 amps is placed between two bar magnets with square ends and surface area of 36 centimeters squared. All right, so let's stop there. Let's go ahead and get an idea of what's going on here. So I've got square ends for the bar magnet. Let's try to draw a little bit better square that. So square ends for the bar magnet. Still not great, but that'll be okay. Surface area of 36 centimeters squared. What that tells me is that each side is 6 centimeters, right? I mean, it's a square, and it has an area of 36 centimeters. Well, base times height for a square here to get the area, so each side must be 6 centimeters, all right? And I've got 2 bar magnets, so let's kind of give a side view here. I got 2 bar magnets, something like this maybe, okay? Each of those sides here, length 6 centimeters, right? 6 centimeters. If the bar magnets cause a 5.6 millitesla magnetic field to form between them, so I've got one way or the other, right? Whichever way you choose to be, north or south, that doesn't exactly matter here. And that's forming a magnetic field of 5.6 millitesla. Like we had said earlier, there's going to be a wire running through it here. What is the minimum and maximum force that we could possibly get? What is the minimum and maximum force that we could possibly get? I'm going to do the maximum force and let you do the minimum force a little bit later on. Okay, so I'm going to do the maximum force, and we'll talk about the minimum force a little bit later on. Maximum force. Now, we want to take this equation, F equals ILD sine theta, and get that F as large as we can. That means we want all of these things, the I, the L, the, all these variables, to be as big as possible. Now, first off, sine theta, we want the maximum force, so we want this arranged at, we want it arranged perpendicular. We want it 9 degrees, and we don't have to worry about that. We don't want it to be at some angle, then the force would be less, right? So I can go ahead and get rid of that here. Sine of 90 is 1 once again, so I'm reduced down to force equals the current times the length of the wire times the magnetic field strength. Now, some of these things are already given to me, right? I mean, they already have told me I don't have a choice. This thing carries a current of 7.4 amps. They also, I'm going to leave length of the wire blank, and we'll get back to that just as the variable here. They also told me the magnetic field strength, right? 5.6 milliteslas times the negative third, right? Now, they didn't tell me specifically what the length of the wire in the magnetic field is, and that's the length of the wire we always deal with. It's the length of the wire in the magnetic field. So starting about here and ending there, the length of the wire that's actually in the magnetic field is what's having the force applied to it, right? Now, from this perspective, from the side perspective, the length, right, is going to be 6 centimeters, right? I mean, that's how tall it is right here. I mean, that distance right there is 6 centimeters. But is there any way that we could arrange a wire in between 2 magnets to get a little bit longer, right, of the length? Well, yeah. Let's come back to our square, right? So I've got a square, something like this, 6 centimeters on each side. What if, instead of running bar magnet straight, or running the wire straight through the 2 bar magnets like this, right? There would be another bar magnet kind of outside of the screen, okay, outside the computer screen about where you are, and the wire's going through the computer screen about where you are there. Okay, instead of running my wire through like that, what if instead I came back and I ran it something like this, right? If I ran it at a diagonal, I would actually get the maximum possible length of wire inside the magnetic field, right? I've got 2 sides of a right triangle being 6 centimeters, right? 2 sides of a right triangle being 6 centimeters, and here, the length of the wire. There's the length of the wire. So what is that length? in this case? Well, if you don't remember any of the tricks with right triangles, we can at least use Pythagorean Theorem, right? L squared equals 6 squared plus 6 squared, right? The two sides, a plus b. So this comes out to be here, just trying to reduce downforce to make it a little bit easier. L equals 2 times 6 squared, right? Excuse me, it's L squared. And then I'm trying to get you back to the trick here, right? Square root both sides, and I get L is equal to square root of 2 times 6, right? Square root of 2 times 6. And that's the trick. Whenever you have two sides at a perfectly right triangle, a 45, 45, 90 right triangle, like this one here is forming, the hypotenuse is always equal to square root of 2 times the length of the sides. And so that's the longest length that I can get in there. So let's take that number. Let's take square root of 2 times 6. Let's substitute that in for L. So F equals 7.4. Square root of 2 times 6. My 5.6 times the negative third. Plug that into my calculator and get the maximum force possible. Alright, so the maximum force this wire would experience here under these conditions, the maximum force it would experience is about 0.35 newtons. Right. Don't forget that you need to have notes over all of this so that I can check them in class. That is your homework while we're in this class reversal idea. So I'll check your notes tomorrow in class, and we'll work some problems together.